So today I'll be covering impact on storage architecture from the point of Internet of Things. So welcome you all. And before I start, so I just want to know how many of you all are involved in developing some sort of IoT solutions or evaluating them for your own company use. Just show of hand. Just raise your hand, whoever is involved in the Internet of Things. Okay, roughly about some 10-20%. Or you might be already knowing about the Internet of Things, but you want to know more. That's what this session is all about. So before I start, a little bit on myself. I am a senior engineer, architect in NetApp under the CTO office. My expertise is on low latency storage and how it impacts the different applications from databases to storage applications. And that's what I've been working on. And in the last 2 years, I have been chasing the IoT architectures. And what I have seen is that there is a reference architecture what we when you start off with, but when you get to the nitty-gritties, the architecture changes a little bit depending upon how you want to extract the value out of that flow, right? So there is a stark difference when you start with the reference architecture and then move to what you want to realize. So this is what you will be getting today in the sense from this discussion. I'll be sharing my point of view on how I see the things and some references that I have got from Industrial Internet Consortium. What are their thoughts and how do they see the IoT architectures evolving over a period of time and how it is affecting the storage architecture as such, right? So I have a brief 4-point agenda today. I'll start with the data growth. So we all know that whenever we are talking about Internet of Things, it's a connected devices, right? They all are exchanging data from one device to another, and then there is an accumulation of data that's happening, and then you try to analyze that, and then get the insight that gives a value to what you are trying to achieve, right? So there is a lot of data movement, and how it moves from the device that is sensing it and how you realize the value. So it's a big flow, and it can't be just a one pipeline, right? There are several pipes in the middle. So that's what I'll be talking about, data growth and the proposed compute model, what we have today, and then I'll dwell into some of the industrial needs for a particular industry. What are the needs for from this solution as such? Just because there is a connected devices in the industry doesn't mean that you are realizing the value, right? There are some things that you need to do, right? So I'll dwell into that, and then I'll talk about a little about some of the data flows, how as I said, the data is coming from several devices. In some context, it could be millions of devices. In some context, it could be large data but few devices. And how do you cope up with that? So you need to have a storage for that, and you need to move the data where it is needed, and then have a compute model that extracts the value out of it, right? So I'll be talking about that also, and then I'll show you the functional split in the architecture, where is what is happening at what place, and how it will evolve over a period of time, okay? Then I'll conclude my talk with some case studies. Okay. So a bit on Internet of Things. So we all know that digital transformation is happening, right, today. It's been happening over a period of time, but it has taken a pace in the last few years to a very high level. And just to set the context, I would like to just read out this. It's very nice. Digital transformation is the integration of digital technology into all the areas of business, fundamentally changing how you operate and deliver value to the customer. So it's all about integrating digital technology into your business flows and changing the way you operate and deliver the value to the customer. That's very key here. You have to deliver value to the customer. Without that, everything goes down. You don't get any value means it's just a word, right? It's just a buzzword, right? And it's also a culture, a cultural change that organizations require, continually challenge the status quo, what you have today, measure it, and challenge that, why we can't better that, and experiment with that, and get comfortable with the failures. This is very important. You need to get comfortable with the failures. Before they occur, you need to predict them and stop them from occurring, such that the end users doesn't see those hiccups, right? It shouldn't, exceptions shouldn't be the norm here. You need to handle them. And that's where the need for harnessing this power of data for competitive advantage is becoming more important. And that's what my talk will be about, how the architectures are being driven because we need to extract the value out of that. And this is happening across all the industries, right? Manufacturing, agriculture, energy, management, all the way up to smart cities, transportation, and healthcare. You have seen this happening, right? And it could be as simple as in manufacturing that you are just tracking through the sensors the product that is moving into the flow in the pipeline, right? Whether it is you're counting those numbers, how many you can produce per hour, and whether there are defects, it's good, it's not good. So you're tracking everything. So it could be in the agriculture, you're basically have cameras that are monitoring some of the plants. If they have a disease, they can detect the pattern for a particular disease, and then they can tell that, okay, this pattern is related to this disease and you need to take action, right? And I could give many examples like that, but so these are the different industries where you see these things happening. And since it involves sensing some measurement that you will be doing on the end product, right? And it involves the Internet of Things, and that's what industry evolution and the benefits that you are seeing now. And the reason I put this slide is because I just wanted to highlight here, these are the different manufacturing benefits in the industrial IoT. I've taken an example of industrial IoT, but it's more or less it's a similar for other consumer devices also, right? And reduced cost. How does it reduce cost? How does it will reduce the cost? Because you are avoiding the failures before they occur. There is no downtime as such, right? You are avoiding the downtimes. So, and then improve the operational equipment uptime and availability. That's what I mean. Like you know that this is going to fail after some time, and upfront you go and replace those devices and then make the operational flow availability at a higher rate. Increase the operational speed. Because you are able to monitor your own devices, you can remove the gaps in your flow, right? You will understand how you are doing your work, and at several point of time, you know that this is the bottleneck that you could remove and increase the speed at which you are delivering your products. Improve the product quality. As I mentioned, this is again related to sensing your device, monitoring them for any failures, and reduce the failure rate. And then improve the safety. Safety as in monitoring your entire equipment or the industrial setup for any safety reasons, then alerting for actions to be taken, right? And so that's what, this is the original, some of the definitions. Enabling communication between devices, people, and processes to exchange useful information and knowledge to create the value for humans. So this was coined by Kevin Austin in 1999, and this has been happening from quite some time, but we have seen the pace at which it has picked up in the last few years, right? Okay, so this is just to give you a feeler as to at what rate the connected devices are growing at, right? And you can imagine the amount of data that is being created with these devices. So here, just to highlight, so in the year 2016, 5.5 million devices have been, connected devices have been added. And if you go to 2017, it's 8.6, a healthy growth, right? Somewhere around 40 to 50% growth. And it is projected to grow up to all the way up to 20.8. So this is a ballpark number. It could be more or it could be a little bit less, but somewhere we are near to these numbers. And if you see here, in this number, roughly around nearly 70% is all consumer devices. And the rest is around 30 to 40% is all in the business use cases. So this is the rate at which the connected devices are being deployed in different areas. The reason I highlighted this is because in the next few slides, I'm going to describe you as to the needs of different industries will drive the architecture. It won't be a similar one, right? After this? This one? See, it is growing at a slower pace than the consumer devices. It's not flat. Nothing like that. It's not flat exactly. It's growing at a slower pace. Then this, if you see this one, it could be around 30 to 50%, but this could be around 10 to 15%. It's not exactly flat, but yeah. Okay, good. Moving on to give you some examples of business use cases, right? The amount of data that is growing. I have put in some examples here just to give you ballpark numbers as to the amount of data that is getting generated, how it impacts the data storage. If you see here, the autonomous vehicles, right? They generate 4 terabytes of data per day, and it's roughly around 50 megabytes per second. That's a kind of data. It could be more also. And this is a number that I've taken from Intel numbers, but it could be more depending upon how many sensors you add. There could be multiple sensors and the cameras and devices, and it could be more as we evolve towards completely a driverless car. And going, and if you see the twin engine, jet engines, so here, a single jet engine has 5,000 sensors today, and I'm just quoting this number, and I know that there is a newer versions of Boeing jet engines which have nearly up to around 10,000 sensors per engine, and they are spitting out data at every 2 to 3 seconds. And that's the kind of data that's coming out, and that could be around 8 for a 12-hour flight. It could be 844 terabytes per day. And roughly 10 gigabytes per second is the rate at which they are generating the data. And if you see the other extreme, the wind farms, this is one of the running example in the sense there are 20,000 wind turbines in a wind farm, and each with 150 sensors. This is a very conservative number. 150 sensors is very conservative. It's much more than that. And that will generate, this entire farm will generate roughly around 30 terabytes of data to be analyzed in real time. And what's important here is that how quickly you take action on that. Because wind farms, they'll be optimally running whenever the wind flows in the direction exactly around 90 degrees to the fan blades, right? And there is a mathematics behind the physics and mathematics behind that. If you tilt, it will be rotating at a lesser speed. So when the wind moves in a different direction, you need to take action. So who will tell that? So if it's coming from multiple farms, multiple wind farms, and you analyze the data and you wait for some time, let's say 10 seconds, 20 seconds, and if you see that it is consistent, then you take action to move all the blades in the directions of the wind, right? To increase the efficiency. So this is the kind of data that's coming in the business use cases and the enterprise use cases, and this is just some numbers for to think over. Now, so all I said that was for the devices that are generating that much of data, and this is a centralized compute model that what we were used to. We had cloud. There were devices which directly sent data to the cloud, and something happened, in the sense you analyze the data and you got dashboards to see that. And going forward, we'll have, this is the proposed model. So in this model, data flows between the device to cloud. There is no intermediary here. And in the next model, it's a distributed computing model. You have cloud in the middle, and the edge is where some compute or the data aggregation will happen. These are the devices on the edge of the network where the data is getting generated, right? And this is the model that is, it's been already mentioned in many of the IoT reference architectures you might be knowing. There are different words for this, edge, for computing, all those things. But key highlight here is that the compute is moving towards the place where the data is getting generated, and there are some reasons for that. Now, having said this, today what I'll be talking in the next few slides is why the IoT architecture is the way it is today, and what are the driving factors for that. What is driving? There are some industrial needs, there are some technological constraints, and if you relax those constraints, the architecture will look totally different. And then that's the talk in the next few slides. Now, I want all of you to a little bit squint on this slide. This is a heat map of industrial sector-wise needs, okay? This has been surveyed and taken across these different industries, manufacturing, smart building, smart grid, and consumer. And these are the different needs and across the different industries. And the red indicates that it's very essential with the higher number. And green it's kind of okay. It's not that urgent, or it's a essential need. The way you read this is, so let's say mobility. Mobility is all about the availability of network support and wireless broadband, and where your objects are moving around and then coming up in a way that they need a lot of network support wherever the objects move around. So that's the kind of requirement. And if you see here, if you see buildings and facilities, right, these are pretty much fixed properties, right? You fix the devices at certain points that are designated, and then you monitor them. You don't need a complete wireless broadband or where the objects are moving in. So the requirement is not that much, so it's 10 here. But for the manufacturing, where your assembly lines have a lot of things moving around, and you need a kind of a wireless broadband support, the kind of network support that you have. So it's very high in manufacturing. And energy, it's again pretty much fixed energy utilities. They're all at a fixed location. What about the consumers? Consumers are always on the move, right? They need a high degree of mobility, right? So this is how you read this graph, this picture. And next one is, I'll touch upon some of the things here. Ultra low latency. So it's 95 here. So what it means is that they can't afford a failure. A decision has to be taken as to whether you want to replace this device very quickly. It could be under milliseconds. For example, let's say that there is a machine tool that is being operated, and this machine tool is generating some more tools, and it's a very high precision machine tool. And if there is a misalignment in the tool, and it will damage all the entire other products that you are building up, right? So you need to predict that ahead of time, so that if there is an impending failure that you need to avoid. A quick decision has to happen. The physics limits, in the sense you can't send all this data to the cloud, right? And then make a call. By the time it comes back, it could be 2 seconds. And you would have seen that your machine tool has already broken. And then the value that you wanted to realize is reduced, right? So it's 95, and then again in the buildings and facilities, you want to take actions on the alarms that are being generated. And energy and utilities, it's less, because there everything pretty much runs, and then in the background when something goes wrong or you want to improve the efficiency, that's where you want to know, take the calls. Consumers is again less. Autonomy is all about disconnected operations. Any sensing device which is generating a lot of data, you need some autonomy for it to take the calls. In the sense, it need not go to the cloud and come back because it can't afford to go. The physics limits stops it from going to the cloud because it takes a lot of time. And that's autonomy in the sense you need to have disconnected operations. Buildings and facilities, again, it's all 100, it's very essential. Security, I need not tell anything about that because it's very essential for anybody to have that. And peer-to-peer communication, this is something in the, it's coming in the future, but in the sense, the edge devices themselves talking to each other and sharing the information. This is slightly, some of the examples are like autonomous vehicles, where cars moving in a line, right? They can exchange the data and find out that if somebody sees a hurdle, the same data can go back to other people who are coming behind you. So the sharing of data. And so if you see here, this is very high here for the consumer devices because people are moving around. If everybody is sitting around here, right? If you can share the data, which is locally, it's more efficient, right? And that's the way you should look at it. And prioritization is something, it's very important in the sense, how do you say that this data is important for me? I need to analyze this data first than this. So you need to have a prioritization for your own data because there is a lot of data that is coming in and you can prioritize as to which one you want to analyze first. And then, so this is, I think, artificial intelligence, machine learning is something in the application space to get the better insights from the data, right? So, summarized way of putting all those things, what I said, I believe everybody knows the Maslow's law for human needs. Just to summarize that in a way, for the IoT needs, right? It's a long life hardware, long-term OS support, and security updates. It's very quintessential, right? You need to fulfill this beyond you go up. And then security update control, how do you manage the updates? How do you do that? Because if you have millions of devices, the update going to all those devices, how do you ensure that it is updated and it's running properly now? So that's the one. And managing that and device management, and then rich device functionalities. What else you can do? Once you have this set in, what else you can do? Can I do the analytics at the edge itself? How do I push that model to the edge? And the cloud offload, since cloud can't handle all those things. And then moving to the edge intelligence. So this is where we might be hearing this one in a lot of other conferences, edge being intelligent, but we need to move in this way, okay? Now this, this slide talks about some of the key factors as to why the architecture is the way today. This is a graph which talks about value of response on the y-axis, and then this is the response time, okay? For the equipment failure, this is how you read it. If you get the information below 1 second, right, it's good enough. You can extract the value out of that. But if it comes after, let's say, 1 hour, it's of no use because the damage has already happened, right? So any industry that is sensitive for equipment failure, right, you should be taking the decisions at less than 1 second's level. And that drives your architecture as to where the data will reside and where you will run the compute and what kind of bandwidth requirements you have for your storage, where if you want to get the decisions to be made under 1 second, right? I'm telling it is 1 second, but when you come to the storage layer, when you break down all those things, it could be milliseconds, right? And similarly, if it is 1 month performance monitoring, this is this is 1 minute. You can monitor and see, you can do the variations. And similarly for supply chain and predictive maintenance. A 1 day worth of data is good enough for predictive maintenance. So 1 day worth of data, you give it to the cloud and then analyze and come back and say whether there is an impending failure after, let's say, 20 days, right? That's a kind of value. So extracting the value is very important at right time. That's the key for IoT architectures. Okay, this is another way of putting that. In a sense, everything comes with the cost, right? Now, when I said you need to have the compute done at the edge, now that's where you get the value. Now, why you want to do that? There could be one is the timeline, another one is the transmission cost, the cost involved in transmitting that much of data to the cloud. If you see this graph here, this is the comparison of total 3-year management and processing costs. This is for completely cloud-only processing and dedicated network cost. And this one is for cloud with the AT&T cellular network. And this one is with the cloud and the edge. Now, the difference here is that when you have an edge, you have the opportunity to work on that data, right? Do you want to send all the data, or you have a way to compress that data in such a way that the information is not lost, right? So that a new data service opens up there. So you could always have if your data is in such a way that if it is a time series data and a lot of repetition is happening, right? You need to understand that whenever the equipments are being monitored, there is something called normal operations, right? And then there is variations that you see for a period of time, and then the equipment fails. So a lot of normal operations are there where you can reduce the data by sending just one shot and then removing all that redundant data. So that's how you reduce. And with that kind of reduction, you will see that the transmission cost is reduced almost by 90%. And if you keep sending the redundant data, you're unnecessarily spending a lot of money for the same value, right? So that's the difference. This is from the cost perspective. And so any change in the communication cost, or somebody tying up with some vendor for very low cost communications, or there is a big change in the way we communicate, again the architecture will move around depending upon how the cost is involved and how you realize the value. Okay, so so this is the proposed today the architecture, right, where you have the devices pushing you the data through some of the protocols, and you have an edge gateway. This basically, it has multiple functions, right? It can map the protocols, or it can act like even the aggregator of the data itself. Now, in the previous slide, I told you that if your the timeline that you have to take the decisions is under seconds, this edge could be almost here. For example, if in industrial safety measurements, like you're trying to find through image processing that if something has failed, or some pattern that tells that this industrial pipeline has broken, you need to take the actions quickly, right? So image processing is at the device itself. So that becomes the edge, right? And you need to process that there. You need to have all the compute, all the artificial intelligence models being pushed to that edge, so that it can take quickly the actions and then move forward. That's the edge that I mean here. It could be different for different verticals. So this edge which is on the near to the devices. So low latency decision making under 10 milliseconds. You need to have this being on the one side independently running on its own. It could support the autonomy, that is the disconnected operations when this network is not there. Peer-to-peer communication, several edge devices. If the network supports, they can share the data. Prioritization, because you know that these streams are coming from these kind of devices, and depending upon the location, you can always make a call that this location which we deployed very recently for this set of farms is of less importance for me right now. because I need to learn about these things. I don't have to push this data directly to the cloud. So you can prioritize that. Once it becomes a reliable source for information in the future, then I'll say I'll raise the priority for this. So this is a very valid wind farm, then I can move the data to the cloud. So you can prioritize all those things depending upon your location and from which devices, what kind of devices, from which vendor, all those calls can be taken. You can tag the data here and then move to the cloud, right? And so this, and then AI ML near real-time inferences can be drawn if the computer is available and the models are available. You need a framework for all that in the sense, where do you build your models? So you need a huge data set. That's where the functionality split comes. That's why you have cloud. Cloud will not go away, right? You accumulate the long-term data in the cloud, you do the batch processing, you refine your models as you start using your data, and then once the model is good enough to, once it is good enough in detecting what you intend to detect in the failures, then you can push the model to the edge. So the cloud becomes more of a batch processing and refining models in this world, and then move the data, move the models to the edge and keep refining that model. That's what I meant. You need to have this iterative process going on continuously, and that's how you get comfortable with the failures. If you can wait, I'll take the questions later. Yeah, if it is clarifying, let me know. Yeah, so any storage that meets these requirements, right? See, low latency means obviously if you're talking about less than 10 milliseconds, right? And your storage requirements boils down to less than 1 milliseconds, you're already in the flash world, right? So the flash is a natural way to look at. And these edges, where do they are deployed? They are deployed in a very harsh conditions, right? So disk doesn't make sense, because if you have vibrations, let's say if it is on the wind farm itself, on the top of the, next to the blades, so there are a lot of vibrations, right? So disk is not suited, and even if you get the high performance disk, so flash is more suited. Now, once you choose the media for the latency, then you need to look at what kind of data that I'm trying to manage there. Is it a small updates I will do, or it's a big large blobs that I will have? What kind of data formats that you will have to manage there? So then accordingly you will have to manage how do you store it on the flash, because flash has some certain life, right? So you will have to optimize for that. That's how the scenario changes. Whereas if you come on the cloud side, right, it's more of a batch processing, right? It's append only. So you can have a less latency storage, but the capacity is, scale is required is very high here. On this one? See, at this level, I would say it's a block protocol, right? And if you any block protocol that that is there, and then any it depends on the, again, as I said, it's what kind of data that you're trying to store. If you know that it is a time series data, okay, and would you like to have a time series database here, or can you avoid that? So these are the questions, because it's a straightforward time series data, right? It's not going to go back and rewrite to the some other original data, right? It will keep on append, it's append only. So any file system, any block protocol which is optimized for append only storage, right, is good for time series data. So those are the driving factors for deciding what you want to put there. And this, you don't know, like today you might be, today you might be deploying two devices, but you will increase it to many more devices. So in that way, you will start with the incremental storage, right? You start with small and then have a scale, okay? So, on the device side, see, in the industrial context, not many devices talk IP. So if you're talking from that perspective, in the traditional world, they all talk some wireless protocol like Bluetooth or Zigbee or something. They are running in a very constrained environment. So not a full stack will be running. So in that world, definitely you need an edge, which can send data to the cloud. So this becomes like a gateway, just a protocol mapper, different devices talking different protocols and then bringing in the data inside. And then once you have the aggregated data, then you can move forward to the cloud. So quickly, I'm running out of time, so I'll just cover this one more slide. So these are the storage requirements on the edge side and on the cloud side. So to highlight that, let's say that I have a network type 4G, 5G. These are the two broadband wireless mobile networks, right? So these are the available bandwidths, and the time required to transmit 1 terabyte is roughly around 15 hours. That I'm saying, if you have a continuous that much of bandwidth continually, right? If it is 5G, it will be 3 hours. And if you have a fiber network, let's say running from your edge device to all the way to cloud, it will be 20 minutes. Still not to the point where we want to be. And if you have an edge, on the last comes, let's say if I have an edge with infinite bandwidth, just theoretically, let's think that you have an edge which can take any amount of data, right? You can do real-time analytics there itself. So that's a way to compare. And any change in this will change the dynamics as to where the data will reside. So these are the some of the other requirements: high bandwidth and low latency.
So in 1000 seconds, you should be able to get 1 terabytes in fiber case, right?
This one? So if there is a maths problem, we'll discuss. That's for the comparison. But you all know that fiber has a better bandwidth, right? Yeah. And that too at a low latency. We'll correct that.
Yeah, just one thing. I'm actually new to Edge. What does Edge really stand for? It's a network protocol, or what is it exactly?
It's a compute hosted system. It's a system where you can host a compute. Yeah.
Okay.
Yeah. Okay. Towards the network, where the latencies are lesser, right?
So why is it real time there? Oh, it's basically communication between the devices and the edge.
Yes, and
not beyond.
If you have the edge intelligence, you would be doing real time.
Right, right.
So
locally, yeah.
All I'm saying is here is that if you try to do it over the network, right, that kind of data, you will be delayed.
Right.
And the value decreases.
Got it. Okay.
Right? Okay. And so this is one of the use case. I'll just wind up quickly. This is one of the use cases in NetApp. This is Active IQ. It's a telemetry data from deployed systems. We have systems deployed all over the different customer places, right? We pull the data from all our systems. This data is all about how are our systems operating. There are a lot of counters. There are 10,000 counters that are being pushed into the cloud. So this is one of the examples where we have data coming from our deployed systems. This is on-premises within the customer environment. Because the data sovereignty issues, right, you can't move the data fully outside. So you analyze that here locally and then move the data through data fabric. This is the NetApp mirroring protocol. And then you push into the Equinix kind of a data center where this is independent in the sense you host the data here and you can connect to any of the clouds. The data resides in the Equinix data centers and connected to all the hyperscalers through high-speed networks, and you analyze the data and get the insights. So this is one of the reference architecture for us which we have done it, and the benefits are here for you to just take a look at this. Storage required is 12 petabytes. If you go for a traditional Hadoop on-premises with DAS systems, whereas with the Active IQ platform, it's reduced to 1.3 petabytes. So this numbers, what it tells is that if you go for a pure cloud solutions, right, for this kind of data, so you might realize the same value at a very high cost, and it might be slower also. And that's a point that is being drawn here, that if you have a hybrid cloud world, it will be much faster. I'll just conclude. I'm coming to the end of my talk. So security, low latency, autonomy, prioritization, and edge intelligence. These are the factors that keep continuing driving the IoT architecture and even the storage architecture. Hybrid cloud analytics is faster than the pure cloud-based solutions. And edge footprint, rather than just being a protocol mapper, it opens up a lot of avenues for adding the data management services. Since you have the data locally and in the compute that is available, you can do a lot of those services. Okay. So with that, I'll conclude my talk. Yeah.
Why did the storage required reduce from 12 to 1? I mean, what was the magic?
So that some of the analytics that was done on the on-premises, right? So that reduces the data, and also when you move the data to the cloud, right? There is some efficiency that is running in the behind the scenes. You reduce the data, you send only the data that is unique. You don't send the redundant data.